Hi. Well, if I want to show anything, I have to use my laptop, so I don't think I'm gonna move too much here. Yeah, because it's a bit annoying. Oops. I don't know. This is not disappearing like it should.
And if you go there, what are the options?
Hide video panel, right? This one? No,
Floating meeting controls. Yeah.
okay.
Okay.
Yeah, thanks. I can still use the mouse. Yeah. Okay.
Just a test. Can you hear us online?
Yes, we can hear you.
Okay, thank you. We are going to start in a couple of minutes.
Here in September. Yeah.
Good morning, everybody. Today we have the speaker is Julia Martikainen. I will do only very brief introduction. She will explain more in detail her career. Okay, so Julia started as IAC not post support astronomer last September. She is sitting in La Palma. Usually she worked there. She occupies of the service proposal we sent to the CAT. And she also is busy with the service proposal. And so she is very expert on the node. She has been working for a long time with node, so she has a lot of experience. And so any question regarding node from IAC can be directed to her. So welcome, Julia. Floor is yours.
Okay, thank you. So thank you for the introduction. Yeah, today I will be talking more about science. So retrieval of dust optical properties in the UV visible near infrared. So yes, first, because I'm a new face here, I would like to introduce myself. So I got my PhD from the University of Helsinki, Finland in 2021. My specialization is in light scattering by dust. So I do modeling, experiments, and also observational astronomy. And I was here at the NOT from 2019 to 2021 as a support astronomer. So I am quite an expert with a telescope already. And I started my first postdoc in 21 at the IAA in Granada. And I was a scientist in this roadmap project, which is a EU-funded Horizon 2020 project. It lasted for 3 years. And I had a key role in the project to retrieve optical properties for Martian dust. And I started in September 25 here as the IAC not postdoctoral researcher. So I'm responsible for the CAT service. Also, I do have time for my own research. So this is what I still also want to keep doing. And also, yeah, the picture, I also have this hobby of taking astro pictures since the skies are amazing here. So this is the outline of the talk. I will be first talking a little bit about the background, then go to the sample processing and the retrieval and validation of the optical constants for the dust, and then a retrieval of scattering properties for the dust. Okay, so let's start with the background. So roadmap name comes from role and impact of dust and clouds in the Martian atmosphere. So this was a joint project between Spain and Germany and Belgium. And the point was to do laboratory measurements and use models to better describe Martian dust and clouds. And our aim in Granada was to create a database of scattering properties for Martian dust. Now, keep in mind, I'm talking about Martian dust here, but these methods can actually be applied for different sort of dust, different materials. So it's not limited only to Martian dust. The first step for me was to retrieve optical constants, so the complex refractive indices. These are really important parameters because these are needed in light scattering and radiative transfer models. So the real part is divided to real part and imaginary part. The real part describes the ratio of the speed of light in a vacuum to the phase velocity of light in the material. And then we have the imaginary part, K, which describes absorption of light inside the material. And then when we know the optical constants, we can use them to get scattering properties like single scattering albedos and efficiencies, cross sections, phase matrices. This can be done using light scattering codes and known particle size distributions. Now, why is it important to retrieve these optical constants using laboratory measurements? It's because in Martian community, typically these values are actually retrieved through observation, so from a spacecraft. And the problem is they're looking at the dust in Mars, but there are multiple free parameters. So okay, they get the let's say the phase function, but they don't know the particle size distributions there because there's no simultaneous measurements at the same time. So they're guessing particle size distributions. And also they're usually using very simplified particle shapes like spheres, spheroids, cylinders. This has been done for 20 years, more than 20 years. And it just, I will show you later, but there is a huge difference what kind of particle shapes you're using for your models. Now, this is why we need experimental data. So we have well-characterized samples. We have constraints on the particle sizes. We know them. We have constraints on shapes because we can take microscope images and we can just construct a model based on that particle shape. So the only free parameter that we really have is this complex refractive index. And then we can combine them with very advanced light scattering models to get the optical constants. Now I'm just going through a little bit of scattering theory very briefly. So what I'm using basically photometry, polarimetry, and spectroscopy. So as you probably know, photometry measures the intensity of the object's electromagnetic radiation. Polarimetry, obviously, the study of polarization of light, and spectroscopy, how much electromagnetic radiation is scattered, absorbed, or emitted by the object at different wavelengths. And what I'm using actually in the study is diffuse reflectance spectrum. So it's the diffuse reflectance from the surface, so it's evenly distributed from the scattering event to all directions. And we are omitting the specular reflection from here. Here is actually a very good graph of different spectra for different colored sheets. So there is a green colored paper sheet, there's a blue and red. You can just see how different the spectra can be depending on the color of the object. Okay, so more deeply into this, what we are seeing is there's a light coming from the sun usually, or a light source, and it hits the cloud of particles or single particle and it scatters. And this light is usually characterized by Stokes parameters. So I will go more into details here. So this scattering event, it changes the state of the light. And this is described by the 4x4 Mueller matrix. It's called the scattering matrix. So what we're basically doing here is, so this, I don't know, here is the final light, basically described by the Stokes vector. And this is the initial light, and it hits the particle or the cloud of particles. And this is the scattering matrix that basically is dependent on the particle material, on the material of the particle, the size and shape of the particle. So this changes the state of this Stokes vector, and this is the final result. And if you don't know what Stokes vector is, and just very briefly, the I parameter is basically the intensity of the light. Then Q and U are the linear polarization of the light, and then V is the circular polarization of the light. Okay. And what we usually use in the light scattering community, we use a size parameter as well. So basically we have different regions here. We have Rayleigh region, meaning that the particle is very, very small compared to the wavelength. Then the size parameter is much below 1. We have resonance domain, the me domain. This is when the particle size is around the size of the wavelength, or the size parameter is around 1. And we have geometric optics region, where the particles are much larger than the wavelength of the light. And then the size parameter is much more than 1. Okay, so in this study, we are actually using the geometric optics because we can do an approximation. It can be approximated with the help of ray optics. So what this basically means is we have here the particle, and we can just simulate the path of the light ray going inside, reflecting, refracting, and we just calculate all the refractions and reflections and the directions, basically. And this scattering cross-section, it can be divided to the ray tracing part and diffraction part. So diffraction part is the forward scattering direction. And in this case, we are not using it because we are looking at backscattered light that we see. Also, single scattering versus multiple scattering, very important. Single scattering here means that the particles are basically very far away from each other. And then in multiple scattering fields, they're so close that we have to use a radiative transfer equation there. And the light is usually here in the single scattering region. They are just the ones scattered by the particle. The light is not going to hit any other particles. There's no interactions between the particles. While in multiple scattering region, like for example, surface, regolith, let's say, the ray is going to hit many particles. So for the modeling part of this study, just to give the general skeleton of it, I first retrieved optical constants, so the complex refractive indices for the dust in the geometric optics region. And we used narrow size distribution for that. Now, what is important to know about these complex refractive indices is that it is not a parameter that depends on particle shapes or sizes. It's actually only depending on the chemical composition of the material. But the problem is, when we retrieve optical constants, we usually use measurements like phase functions or reflectance spectra, and these measurements are dependent on particle sizes and shapes. So it's important when you do this kind of a retrieval to do the modeling correctly, have the correct sizes, have the correct shapes, to get the optical constants correctly. And then when you have them, since it's only material dependent, you can apply them for different particle sizes. It doesn't change, since the material is the same. And here I just have from Lucy et al. A picture. This is glycopyroxene. It just shows. So this is the same material, but just with different particle sizes. So you see the only thing that changes here is the level of the spectrum. It's not changing the features of the spectra. Then when we have the optical constants, then we have to know also how well can they be actually used on real Martian regoliths. So they have to be validated. And after validating them, we retrieve the scattering properties. So single scattering, albedos, and efficiencies, and so on. And this we did from measured scattering matrices. And I will explain this later. It's a bit complicated. Okay, so samples. This is an important part. What samples to choose? What samples represent the surface of Mars or the atmosphere of Mars? So initially, we had two samples. We had JSC Mars 1. This was from the Jet Propulsion Laboratory. And we had MMS2 simulant, which was from the Martian garden. So the JPL actually has an MMS sample that they then took and they added some iron to it. So it just has a higher iron content. And you can see here the description of the materials inside. And so we had very large particles actually that we had to process. So processing of the samples. This was done at the Instituto de Cerámica y Vidrio in Madrid. They had to go a rigorous process, and this took like months, 3 months, 4 months to get the size distributions that we wanted. This was quite difficult. So first they went through milling and sieving, decantation, centrifugation, because we wanted very well-characterized narrow size distributions. And the problem with this is usually that particles, they tend to stick together. And larger particles, usually these small particles stick to the surface of them. So you have to get rid of them so that you have clean particle size distributions and not aggregation there. So finally, they produced actually 2 different particle size distributions for each sample. This 63 to 120 to 40, and I'm showing here also the size distributions, final size distributions for them. But then we noticed that there was a problem with them when we compared the reflectance spectra. As I explained earlier, the spectra features cannot change if the material stays the same, only the level should change. And here they are, different size distributions of the same material. They are interlapping or they have very different features. So this was an indication that something was wrong, that there was a different composition between these samples, which shouldn't be the case. So when you really look at this, we notice that there was this, in the bigger particle size distribution, there were these larger quartz particles that were not then in the smaller particle size distribution. So we had to actually discard the larger particle size distribution, because for the modeling, we need a homogeneous sample. Okay, so let's go to actually now the retrieval validation of the optical constants. So these were our final samples. We added one more. We had the Mars global simulant sample as well, just to have very different characteristics for the samples. And here you can see the size distributions for the, I think, L sample. And the spectral reflectance spectra was measured in Granada. You can see there is this kind of drops. This is artificial. This is from the instrument changing from one wavelength region to another. So this had to be smoothed out. But you can really see the different spectral features here for the samples. You see, for example, the MMS2 was very, very red. And the wavelength range was from 200 to 2000 nanometers. Now they have actually bought this similar kind of spectrometer at the IAA, and the range for that is 200 to 3000 nanometers. So it's a bit bigger now. So particle shapes, then it's important we get also field emission scanning electronic microscope images for the particle shapes, just to be sure that we are modeling them correctly. So you can clearly see spheres probably don't work here, cylinders. So we decided then to go for these Gaussian random sphere shapes that are quite okay when you look at the microscope images. And how this modeling then works is we first do the scattering computation single scattering properties using this series 4 code that simulates light scattering by Gaussian random sphere particles that are much larger than the wavelength of the incident light, so in the geometric optics region. And then we have the measured particle size distributions of the samples. So we just average, we first compute for many, many different particle sizes, and then we average over the size distribution. And then we put that into a multiple scattering code to simulate the surface. So basically, we're just simulating the setup of the experiment. And we see the reflectance from the surface. This is the final product. And we just compare the modeled reflectance to the measured reflectance. And we can iterate the optical constants until we get matching values. Yeah, these were the first results using GRS1. We assumed 15% maximum uncertainty for the measured reflectance, just to show or see how much the retreat optical constants would change. And as you can see here in this image, when you take a close-up picture or zoom, you can see that there is this surface roughness. And the thing is, with this particle, we couldn't, it's quite smooth. So we couldn't really simulate properly the surface roughness. So this might have actually an effect. So then we tried many different shapes. We tried spheres, just because a lot of people are using them, just to see the difference. We tried these angular particles, polyhedras, and the spiky GRS2 particles. This is actually, according to previous studies, could work for simulating the surface roughness of the particles. And here are the results. And we noticed that the absorption, so the imaginary part of the refractive index, it increases when the particle irregularity increases. And also for this retrieval, we assumed that the real part of the refractive index is 1.5, because otherwise there would have been multiple free parameters. And then, of course, we had to check if it's okay to do this assumption, if the absorption or the imaginary part would be affected by this. So we also repeated the computations for different real part of the refractive index. And we noticed that for this kind of a retrieval from the reflectance spectra, it's not important. within the range of silicate materials, 1.4 to 1.6, the real part in this retrieval didn't matter too much. Okay, so validation. Now, question is, how well do these analogues actually represent Martian surface? And also, I'm showing you a picture here. So the values that people have been using for 30 years from Wolf et al. For the refractive index for Martian dust are in the blue curve, and our results are here. So they are very different. So we want to check what is going on here. So we actually obtained NOMAD UV spectrum. So NOMAD is an instrument on board ExoMars. And we selected region with well, relatively high visible albedo so that we just get the effect from the atmosphere as low as possible. And so that there were no clouds or there was no dust in the air from the zenith angle. And then we carried out bidirectional reflectance computations using this model. So this was just the first test. I just tried one particle size distribution, 20 to 40 micrometers, just to see which sample actually looks the best. This black curve is the real reflectance spectrum of the surface of Mars. And we saw that the MMS2 was the closest to the surface. So then this is the sample that we selected to proceed with. And we checked from the literature that the previous studies had shown that the particle sizes on the surface, these kind of bright areas, were below 100 micrometers, maybe more specifically 2 to 40 micrometers in this bright region. So then in order to better simulate the surface, we create a broader, actually not normal size distribution, but the power law size distribution from 2 to 40 micrometers for the MMS2 analog. And then we also did this computations using the refractive indices that people have been using for decades. So these are the results. It seems like our values here are working quite well, especially at longer wavelengths. So the power law indices that we used were quite low because you have to remember we are looking at surface, so there must be larger particles there as well, according to previous studies. And then this was the best fit that I could do for the values in literature with power law index 3. This means that there's basically no large particles there, which is not really consistent with previous studies. We did notice that when going towards UV, then the differences will increase between our values. So maybe in the UV, these values could work. But when you go to longer wavelengths, then you probably are using too much absorption there. Then we, of course, were thinking, why do we have these differences with the literature? Maybe, of course, different particle shapes makes a huge deal here, which is why we have these differences. And also, well, they did their retrieval based on observation, so maybe the size distributions for them were just not right. Or there is a compositional effect, as we noticed when we were processing the samples. Maybe some materials, they get lifted up more because they're looking at atmospheric dust. This means maybe the material is very different from what is on the surface. Yeah. And this is also like an open question. To what extent could this compositional separation operate on Mars, for example, compared to surface and the atmospheric dust? Okay, so let's now go to the retrieval of the scattering properties. First, the scattering matrix measurements that we had to do in order to be able to retrieve the scattering properties. We used the Cosmic Dust Laboratory in Granada. This is a device designed by Olga Munoz. And how this basically works is we have here the sample in the middle, and we have laser. And the laser hits the sample here, and it goes, of course, to all the direction light. Then we have a detector that goes around here, almost 180 degrees, and measures the intensity and polarization of the light. And we have also a monitor that is monitoring the target if there's any clumps or problems with the sample itself. So we have two ways of doing these measurements now. this one was done using the aerosol generator. So the aerosol generator is pushing the sample basically to the beam. It goes, it's a stream of particles, and there in the bottom there is a vacuum cleaner that then sucks the particles in. So it's going, the light is going through a stream of particles. And there is also now an acoustic levitator that can be used to levitate particles. What we measure are the scattering matrix elements, F11, F12, F22, F33, F34, and F44 at 2 different wavelengths for this study. We can go to different wavelengths depending on what is needed. Here we used blue and red light. For the modeling part, to retrieve the scattering properties, we use these measurements together with the retrieved refractive indices, and we use a scattering database, which I will talk about soon. And the samples we used for these measurements because we wanted to actually get the scattering properties for aerosol dust in the atmosphere. So the scattering, well, the size distributions were a bit different. So we had S, M, and L size distributions, just to have a bit more variation. I don't have a lot of time to go through this, but we had, these are the scattering matrix measurements that were carried out. So this is on the left side, these are in the red light, and these are in the blue light. So what interests you more probably as an astronomer would be the first 2 elements here, these first 2 rows, because this is the phase function, and this is the degree of linear polarization. And I guess like the most important features for these would be here, this is, so you have to remember we are looking at, we use scattering angle in the laboratory. So scattering angle is actually the opposite of phase angle. So 0 scattering angle, this is forward direction. So this would be 180 phase angle. And the opposite 180 scattering angle is backscattering. So this is 0 phase angle. And what is important to see, for example, here we have this is a forward peak. It's caused by diffraction by larger particles. Also, the slope is very different depending on the particle size. And then we have here the degree of linear polarization. So this is important features, the negative polarization branch. And this is mostly caused by small particles. And also the inversion angle is depends on the particle size. Okay. So now the modeling approach, there's really 2. It's either you compute the scattering properties from the scratch using advanced scattering methods. Well, because we have different particle size distributions, we have different materials. This is computationally very heavy. And if you change a parameter, you have to do it again. So then the second approach would be to use a scattering database to retrieve the scattering properties. So these databases, they usually have pre-calculated scattering properties over a wide range of particle sizes, refractive indices, and wavelengths. Then the question is, then how do you select this database? Because different databases have computations for different particle shapes. For us, it's easy because we have the laboratory measurements. We can just directly compare and select the best database. So the databases that we considered in this study was the TAMUDAS 2020. This is very new. So it is for very irregular particles, these hexahedral particles. And then we compared it with triaxial ellipsoids that a lot of people are also using. The triaxial ellipsoid database, you can download it from the link. So it has pre-calculated data for 42 shapes, different axis ratios, refractive indices, size parameters, 34 different shapes, spheres, prolates, and oblate spheroids. And then we have the hexahedral database, where you can also download it from the link. So each data point in this database contains an ensemble of 20 hexahedral particles. So computations for that ensemble. And there's a short wave and long wave domain. So if you do, for example, I don't know, protoplanetary disks, you may actually want to use the long wave domain. And in this case, I'm using the short wave for our wavelength range and sizes. And the defining parameter here is the sphericity parameter. So by changing this, you can change the mixing rate of different irregular shapes within the ensemble. So it goes from 0.0 0.7 to 0.78. And smaller value here means higher aspect ratio, so you have a more irregular particle here. And usually, since we are talking about dust particles, these are very irregular particles, so the lower value, the better. And our first test, just to test these two databases, was actually using palagonite. We had already these measurements done years ago, so this was a very easy test. And we also could compare it with spheres. And there was a lot of studies before about this palagonite using the triaxial ellipsoid database. And this gave us the value for the complex refractive index because the best fit was already found by Merikallio et al. So just to use this refractive index from the previous studies, we can actually compare how different shapes can produce the scattering matrices. Now, I don't know how well you can see, but the spheres just don't work. The problem with spheres is that you can't simulate scattering by irregular dust with spheres because spheres have very specific scattering behavior. You need spheres to model spheres. Then these triaxial ellipsoids, they could actually model quite well. I think it's the green curve. But of course, you see there were some discrepancies to the measurements. And then we saw that these hexahedra particles and samples, they actually produce really well the measured scattering matrices. Very also. This is what we then selected to use for retrieving the scattering properties of the dust. Now let's go to the actual dust, the Martian dust. Here I have the large particle size distribution for JSC Mars 1 with a sphericity value of, different sphericity values just to check what sphericity value is the best. And we came to the conclusion that it has to be 0.71. We, of course, didn't carry this out for all of the size distributions and all of the samples to see what works the best. And here, really, you have the complex refractive indices already. You have the measured size distributions. All thing that is free is really the sphericity value. And here I compared the hexahedras to spheres. And as you can see, spheres really don't work. Yeah, you can't, it's just impossible to model polarization, for example, with spheres. And even this phase function doesn't, it doesn't look good. Then, of course, we had to carry out sensitivity tests. We changed the real part of the refractive index just to see how much it changes the model compared to the measurements. And we can also fine tune it like this. And this was very important. We also want to test how our retrieved imaginary part works. So for the M sample, you can see if you increase the imaginary part for the polarization, degree of linear polarization, it seems to work better here. But then, of course, the negative polarization branch, you can't really do anything about that. So maybe now you could say, oh, maybe, we need more absorption, but the values are wrong. But the problem is that since the material stays the same, you have to use the same refractive indices for the large particle sizes as well. So if you change it for the small, you have to change it for the large as well. So this happens when you put higher absorption. The model just completely blows out of proportion. Now, this is because large particles, they are more sensitive to refractive index because light travels longer inside the particle. So when you do refractive index retrieval, it would be very, very important to actually do it using larger particles because they are more sensitive. And this is probably also the problem with the values in the literature because they are using very small particle sizes and they have to assume very high absorption. But then these values just don't work if you're using larger particles because they are too high. Now you're probably asking why I'm not showing anything about the S size. Now this is the S size. What we learned from this, that sometimes not being able to model your measurements is a result in itself. We realized here that the models you can't model this S sample. And then we started to think, what is going on here? And if you really look at the measurements, you see a diffraction peak here. And this is caused by large particles. Now, this size distribution is supposed to be below micron. So this is not supposed to be here from the measurements. So this means that there is particle aggregation. And we came to a conclusion that in natural conditions, certain particles under 1 micrometer size, they stick together. This doesn't exist in nature. So this is what we saw in the measurements. And the model shows this actually correctly. It's supposed to be flat, the forward part. Okay, so now that we have used or validated the hexahedron model, then we now could retrieve the optical property database from 200 to 2000 nanometers. And just to summarize, we have created an optical property database for Martian dust using 3 different Martian analogues. This data is all available at the Canada-Amsterdam light scattering database. We use dual validation, so we use diffuse reflectance spectra and also full scattering matrix measurements for this. And this methodology, it can really be used for other planetary materials as well. And if I have a little bit of time, I just want to show you, this is the Canada-Amsterdam light scattering database. If I can maybe, okay. So here you can see just the different samples, and the results that I have just shown are also here, and all the measurements and all the size distributions if you're interested. And it's not only for the Martian dust, so we have so many different materials here. Unfortunately, we only have to have the optical properties for Martian dust because there hasn't been time to retrieve for other samples. Okay, thank you.
Thanks a lot for your talk, Julia. Now we're going to move on the questions, but before, let me just remind to all the PhD students that are in the room to come here at the end so I can just check their presence. And for those on Zoom, please write a message to Seminarios or send an email so I can just check. Okay, let's move back on the talk, on the science. Do we have any questions? Or in the chat, you can also write or activate your microphone.
Hi, Julia. Nice talk. First of all, thanks for using wavelengths in your plots, not the crazy wave numbers that laboratory people use and we never understand.
Yeah.
My question is related to the methodology you're using. If you can apply, for example, these two samples of real objects like Bennu and Ryugu.
Yes. So this is actually what's going to happen is they're going to get samples from Ryugu and Bennu, and they're going to do the measurements in Granada. And I'm actually supposed to be the one to do the optical constant retrieval for them.
But you have the conditions to maintain the samples. No.
No, that's why they have to go to other laboratories first, because I don't think there is a way to preserve them well.
And you can assure that the properties will not change after interaction with the atmosphere, or?
That's a good question. I don't think it should. I don't think it's not so sensitive.
Because they will oxidize very rapidly, for example.
Yeah, that could be. That's something they need to think about when they do the measurements.
Thank you.
Other questions?
Just 2 questions. Can you get the optical constants more to the red, say 20, 30 microns, just the James Webb range?
No, the problem is the wavelength range of the instruments right now. I mean, if you have reflectance spectra for all that range, then yes, you can.
But do you have those data in your database?
No, because
You usually stop it at 2 microns.
Yeah, 3 microns actually nowadays.
And the other question is, how many carbon-rich particles do you have in the database? I think that just a minority.
I think there is a few samples, yes.
But most of the database is about oxygen-rich particles, no?
Yes.
Okay, thank you.
Other questions?
No, just a small question. You mentioned something about the aggregation of particles.
Mhm.
that are impacting the optical results?
Yeah.
And have you considered the possible aggregation, the particle with other components of the Martian atmosphere, CO2? Because in the Earth atmosphere, it happens that the atmospheric molecules
Mhm.
aggregates dust particles, and it changes a lot of the optical properties. Have
No,
you considered something like that?
No, so we haven't considered this. Of course, we would love to have a sample return mission, to be honest, but this is currently the samples that we are working with are the ones that are produced here on Earth, and these are the best samples that we could find.
Okay, we have a question from Julia De Leon. If you want to activate your microphone.
Yes, I prefer. Do you hear me well?
Yes, we can hear you.
Hi, Julia. Very nice talk. As you know, I'm very interested in your work. Any clues on what would be happening with this contamination that you discovered of these larger particles on the pellets of the smaller particles?
You mean
Yeah.
this one? Yeah,
Yeah.
so we had different kind of two different kind of compositional separation. We had this one. So we did an X-ray diffraction analysis, which showed that the material had changed. So
And the other one where you
and the other one
basically
was
had
with the
this, yeah.
with the larger quartz particles, actually. We had this one.
Yes.
I think it's just because from the initial sample, there just happened to be quartz particles that went through the sieve. And you see them here. But then when you put them through another sieve, they get stuck. And then you have a more homogeneous material. And we
Because
also
the process to separate the samples it seems very complex, and you mentioned that it took months. So I'm surprised that in the end you have to discard one of the samples because it's not usable.
No.
Just curiosity.
Yeah, it is very difficult to characterize these samples well and produce them in the laboratory. There are a lot of things you have to consider. Then you find out that there's compositional separation, and in the end you have to try to find a way to go around it.
And I have another question, if I can.
Yeah, sure.
Okay, so when you showed the reflectance spectrum of the 3 Martian analogues, and I don't remember the slide, sorry, that one. Do you know more or less or have an idea of the composition of the 3 samples or the main mineral dominating them for each of them?
I think I had them here. I have actually
There.
I have tables of
Okay.
them in my paper, but I just didn't put it here because it's a chemical formula. So if someone is interested, you can check my 2023 paper where we have all the tables of the
Okay, I will. Thank you.
Any question here? Or in the chat? Well, if I can, I have one very curious question. In the future, do you have other targets apart from Mars dust and Mars samples and asteroids? Do you want to explore other objects?
Yes, so the people in Canada would be very interested in collaboration. If you have any materials you're interested to study, then please let me know.
Okay, thank you. Well, if there are no more questions, we can thank our speaker again.
Hi.
Fernando.
Oh, nice to meet you.
I ask you because do you plan to get the optical constants for additional carbon materials, particles?
Yes, we are.
I know
actually
you're
thinking.
thinking about that.
We were talking with Tanya about that we would like to get some carbon here. Yes, and get optical constants.
Because we use the optical constants to model,
Mm.
for example, James Webb spectra or pictures
Yes.
of planetary nebula.
Yes, exactly. I've been working with Palmira Jimenez. She's also working on for protoplanetary disk, and she would need this.